Hello, today we're going to take a look at rational functions. Our objectives are I can write equations for vertical and horizontal asymptotes. I can transform the graphs of 1 over x and 1 over x squared. And I can analyze simple rational functions using transformations of 1 over x and 1 over x squared. All right, so you might be asking yourself, what's a rational function? So I ask you to go back to just what's a rational number. And so we talked about this earlier. Rational numbers, I want you to think fractions. Okay, so rational numbers are any number that you can write as a fraction. So you can write 3 as a fraction, 1/3, 9/5. Any of those are considered rational numbers. So a rational function, I want you to think of a function that's a fraction. And in particular, it's a polynomial in the numerator and a non-zero polynomial in the denominator. And of course, it's important that it's a non-zero polynomial in the denominator because we cannot divide by 0. A lot of times these rational functions will have your asymptotes, okay? And we specifically talk about horizontal and vertical asymptotes. So let's just refresh ourselves with what a horizontal line is. A horizontal line is always y equals. So the green one is y equals 1, 2, 3, 4. And the blue one is again a horizontal line, so it's y equals -1. And then the red line is 1, 2, 3, 4, 5, but since it's vertical, it's x equals. So it's very important that when you're asked to write equations of asymptotes, you don't just write 5. You need to write x equals 5 or y equals 4, things like that. So I'm going to look at some graphs that have asymptotes. One of the first ones is this shape here. When you're looking at your parent functions, hopefully jogs the memory of what this is called. This is an exponential function. And it's in the, e to the x is my favorite exponential function, or 10 to the x, 3 to the x, any of those are all considered exponential functions. So you might be a b to the x, you might be used to seeing y equals e to the x. Those are all examples of exponential functions. And you can see this one has a very particular asymptote. It doesn't look like it's ever going to get lower than that number right there. So this guy has a horizontal asymptote, so we know it's y equals, and it looks like y equals 2 is the equation. We're also going to talk about domain and range. So remember, the domain are your x values, and you can see here the x values taken on by this graph are all real numbers because there are no x values that can't happen. All right. Now, if you see a vertical asymptote, then that tells you right away there's some x value the function can't use. So in the range are our y values, and so we know our y values, if we look at our graph, are all the numbers above 2. So we might say y is greater than 2. We might say from 2 to infinity, making sure not to use the equal sign and not to use a square bracket on 2 because we are not including 2. We're approaching 2, but not hitting 2. All right, here's another graph that we're going to pay a lot of attention to in this unit. This is our 1 over x graph. This is our basic rational function here. Okay, so this is the guy we're going to transform. We're going to move him up, down, right, left, flip him over. So take a look at that parent graph and make sure you know what it looks like. It has two equations of asymptotes. You can see that it has this line right here, which is the y-axis, and it has, or sorry, the x-axis, and it has this line right here, which is the y-axis. And so our equations for our asymptotes are y equals 0, the horizontal line, and x equals 0, the vertical line. And its domain is all the x values that happen, which go from -infinity to 0, and again from 0 to infinity, right? But does not include 0 because you can see the asymptote. And our range are all the y values taken on by this graph, which are from negative infinity to 0, and again from 0 to infinity, because you can ride this curve all the way almost to 0 and down to negative infinity, and you can ride it all the way up to positive infinity, but you're not ever going to touch 0. All right, and this is our next parent function we want to take a look at, which is called the inverse power function. And this one is, in particular, 1 over x squared. Okay, I call this my volcano graph. Kind of looks like a volcano erupting. And it, too, has asymptotes, the same ones that the last guy had. So the y-axis here and the x-axis. So our equations of our lines are x equals 0 and y equals 0. And the domain is still the same as the 1 over x, so it's still going from negative infinity to 0, and again from 0 to infinity. But the range, as you can see, are now only the positive values. So all positive numbers, or I would just say from 0 to infinity. You could say y is greater than 0. However you want to write the range and domain is kind of up to you. All right, so now let's take a look at transforming one of these graphs. So I see that I have the 1 over x plus 2. So since that plus 2 is happening outside 1 over x, we need to, so that plus 2 is going to move everything up 2 units, which means it's going to move the horizontal asymptote up 2 units. So now instead of being at at the x equals 0, it now will be moved up, sorry, to y equals 2. So instead of being at y equals 0, it's now moved up to y equals 2. But there's no left or right transformation, so the vertical asymptote stays the same. And we draw in our, I call this my double boomerang graph. It kind of looks like a boomerang. There's 2 of them. So it's approaching both the asymptotes, but not reaching them. And so my equations are the red one, which is my horizontal, is y equals 2. And the vertical one did not change from its parent function, which is still x equals 0. All right, let's try another one here. So I have the graph 1 over x plus 5. And so that plus 5 moves it to the left 5 units. So I'm going to go over 1, 2, 3, 4, 5. And so I'm going to take my vertical asymptote and move it over 5 units. But my horizontal does not change. And then again, I draw in my double boomerang graph looking thing here, approaching my asymptotes. And write my equations of my asymptotes. So again, the red one is my horizontal, which is the y equals 0. And now the x has been moved over, so it's x equals negative 5. All right, let's try one more here. I've got the graph 1 over, or negative 1 over x minus 3 squared. So now because of the squared, my volcano looking graph, the minus 3 means it's right 3 units, and that negative means it's reflected or flipped over x-axis. Okay, so instead of it being in the first and the third quadrants, it's now going to be in the second and the fourth quadrants. Of course, that's before you transfer it. So it's reflected, it's in the second or the fourth quadrants, and then it's moved to the right 3. So I'm going to take my vertical asymptote here and move it over 3 units. So we'll say that's 1, 2, 3 units. And I'm going to flip it, and it's going to look like a volcano. So again, remember it's going to be bounded by the line y equals 0 and the line x equals 3. So x equals 3 is our vertical and y equals 0 is our horizontal. Again, it's very important that you're writing equations. All right, now we might have a rational that looks like this, 3x plus 8 over x plus 2, and we need to divide the two polynomials to get it into our parent graph. So 1 over x is what we're looking for, with maybe a plus something at the end or in front. So we're going to go back to our unit on polynomials, and we're going to do polynomial division here. X plus 2, so x goes into 3x 3 times. Multiply that back through, so I have 3x plus 6. Subtract, I get a remainder of 2. Remember how we write our remainder? As plus 2 over x plus 2. So my new equation is 3 plus 2 over x plus 2. So that tells me that my graph is that 3 in front, it doesn't matter that it's in front or behind, tells me that that graph has moved my horizontal asymptote up 3 units, and my plus 2 here means it went left 2 units. So it went left 1, 2. And that 2 is a stretch factor. Basically all that does is it pulls the boomerang further away from the where the two asymptotes intersect here. But graphically, we're not going to really ask you to show that. It's just kind of a stretching away from that kind of center point there. You could grab it using a T-chart if you wanted, just so you got a point so you could see it. But when we're just asking you to sketch it, we're going to be mainly looking for your asymptotes, and we're going to be looking for the right quadrants. And so we're not too concerned about this vertical stretch factor here. All right, let's try another one of those guys. Maybe stop the video, make sure you can do this one. Okay, so hopefully you're back, and I got my division to be 4 minus 19 over x plus 5. So graphically what that's going to do to us is we're going to take our horizontal asymptote and move it to 4, y equals 4, and we're going to take our vertical asymptote and move that to negative 5. All right, I'm going to take all and move it over, and now I see that this negative tells me it's going to be flipped. So what I would have put in those quadrants, it's now going to flip to the other two quadrants, and then again that stretch of 19 just kind of brings it further away from the center of the asymptotes. But again, just put it in there and I'm good with that. All right. Hopefully this is enough to get you through the graphing piece. Now let's write an equation. All right, so this says write an inverse square function that has an asymptote of y equals 3 and x equals 2 and passes through the point 3, 12.5. Okay, so if it's an inverse squared function, here is my parent graph. If I know it has a horizontal asymptote of y equals 3, that means my graph has been moved up 3 units. If it has a vertical asymptote at x equals 2, that means inside the function here, it is going to be moved 2 units over. Okay, so just a little technical difficulty there. My board started blinking at me. All right, so then I get to go x minus 2 squared. All right, and this is an a, kind of looks like a 9, but I'll put an a here because we don't know what the stretch factor is. But we do have an x value and a y value, so let's put those points in. 12.5 equals a over 3 minus 2 quantity squared plus 3. Move that 3 over, so now we're looking at 9.5 equals a over 1 squared, and therefore a must equal 9.5. So now I have 9.5 over x minus 2 quantity squared plus 3. And again, as far as the graph goes, you can see that we've got it sketched. We got our asymptotes um, put over here. Now it's kind of not in the best to do fractions and decimals, so you might, instead of see 9.5, you might convert that to a improper fraction. So that might be looking at 19 halves, all right? Because 9 is the same. So it might be written like this in your book. But either way, it's still a vertical stretch factor that we're not really putting much emphasis on when we actually sketch it. If we did a T-chart, they'd be more important to us, but we're just roughly sketching them. All right, hopefully that's enough to get us some work for tomorrow. All right, have a good night.